Right, I don't see anybody coming in the room, and we're pretty full, so I'm going to get started a couple minutes early. We have a lot of stuff to cover. My name is Todd Holmquist Sutherland. I've been working as part of the Windows Azure Service Bus team since roughly 2008 when I joined Microsoft. And I'm here today with Paolo Salvatore, who's from the Azure CAT team, the customer account team. And Paulo's going to give a demo toward the end, but I'm basically going to talk to you for roughly 45 minutes about the subject of the Internet of Things with the Azure Service Bus. One thing I'd like to do to get started is to just find out how many people in the room have had some experience with professional embedded development. Just see a show of hands. It's quite a few people. How many people have played with an embedded development kit of some kind? What about built backing systems for a production M2M or IoT application? Fewer people. Okay, that's maybe a bigger, scarier proposition. What I'm actually going to be talking about a lot today is what happens on the back end. We're going to talk a little bit about the client side, but mostly about backing services for embedded devices. So I'd like to give a little bit of an understanding of how I think about and how we think about the Internet of Things. So this slide sort of talks about how everything is getting smart. I see this kind of slide quite a bit. And actually, it's kind of interesting because you can see that it's affecting almost every industry out there. The Internet of Things is having an impact, and we're seeing this from a Microsoft perspective in terms of the kinds of customers that we interact with. But when I look at something like this, I don't really know what it means. I mean, for me, the idea that everything is getting smarter is a good thing. It's a good thing. Is smart the new dumb? At some point, we'll have to take smart off because everything will be smart, and then there'll be a new smart. What is it really about? You know, what is the difference? What's the new development around the Internet of Things? And so this slide is interesting, but it doesn't really talk about that. I'm going to give a little bit of an introduction just to talk about what I think the Internet of Things is all about, based on the kind of customer engagements we've had, say, over the last year and a half, sort of what it really is today. So thinking about this at a high level, the Internet of Things is really about a couple of different key trends. One is about the business of data-driven insight. So there's kind of the data side to the Internet of Things. And from that perspective, it's important to think about the way that we get money and generate value out of information. Ultimately, data turns into information, and information gets processed and turns into some kind of insight that we can use to make decisions. There's a couple of different aspects to that. One is kind of making more efficient use of resources. You can think of this as being about reducing cost or reducing the environmental impact of the things that we do. An example of that would be power management in the buildings and data centers that we operate as a company. So Microsoft does quite a bit here. And you may have heard about some of the work we've done about making our buildings on campus smarter back in Redmond. Another thing that we do around generating insight is to provide more targeted products and services. It's kind of the other side of the equation. So rather than just reducing costs, we have a way to engage customers and to develop products that are more targeted for their specific needs. So this has an opportunity to increase revenue and to increase the social impact of the things that we're building and doing. Really, the generation of insight here is about increasing value based on the data that things can provide us. So what the Internet of Things is really doing is it's providing a new source of raw material for that insight pipeline, and therefore a new source of raw material for different and new kinds of business that are coming from the Internet of Things. So that's one aspect. The other aspect, which is often overlooked, I think people tend to focus on the data aspect of the Internet of Things a lot. But certainly from the point of view of the service bus and the messaging infrastructure we have in the cloud, one of the things we see a lot of focus on from customers is how do I enable the other part, which is how do I reach out and interact with things out in the real world, the sort of command and control side of the picture. So what I'm calling here enabling action at a distance. From that point of view, data isn't the only raw material that's being unlocked. The other thing that's being unlocked is this ability to act remotely, automatically and intelligently, both for efficiency purposes, the ability to do things like tune the way a machine is running, or increase the efficiency with which a sales team in a store can meet the needs of customers coming into the store, both for reasons like that, as well as enabling new kinds of engagement with customers that go beyond the ways that we can do that today. So today, engagement opportunities don't really exist in the form of physical products that are interacting with customers outside of the context of these smart things, tablets, phones, PCs, things like that. What we're doing is we're making the everyday objects of our lives opportunities to engage with customers. And that allows us to take that engagement beyond the point of sale, beyond the point where we've actually delivered a thing to the customer, and into the customer's life, into the life of the business that we're serving or the individual that we're serving. So things like preventative maintenance, or best practices guidance on how to use our products, or proactively being able to go out and tell a customer that they might be able to take advantage of some new product that we have based on understanding how they're using our existing products. And then doing things like remote servicing so that we can fix problems without having to send people out into the field or without having to inconvenience customers. So these are some of the things that come from this kind of enabling action at a distance piece of the puzzle. And ultimately, that's coming around to a new way of thinking about customer relationship management. And you will probably hear this term, some of you may already have, product relationship management. It's all about using products as a point of presence with your customer, for your business to be a point of presence with your customer. Okay, so let's make this a little bit more concrete. Here's an example of an implementation of a system that has both of these aspects, both in terms of collecting data from things in the real world, as well as reaching back out and interfacing with customers and generating these kinds of opportunities I'm talking about. Door-to-door navigation. This is something that some of the smart car vendors are working on. And just to walk you through the workflow at a high level, you put the details of an upcoming trip into your calendar application. That application shares data with the door-to-door navigation service. Before your trip, you get notifications on your phone, indications of when you should leave based on traffic and weather, whether you need to refuel your car and how that might impact when you have to go. Notifications come to your phone or other devices. When you start your car and actually get in your car already knows where you're going and can display a map, have a map ready. It can recommend a different path based on traffic congestion or construction that's going on. When you get near your destination, your car could help guide you to a parking spot that might be open and automatically pay your, the parking meter if you have a pre-configured account set up. When you get out of your car, the navigation transfers to your cell phone, your mobile device, and now you can actually get walking directions that allow you to complete your journey all the way to the end destination. And when you're all done, the system will help you find your car. So one of the interesting things about this picture is that it's not just an in-car system, it's a system that spans multiple screens. So this is kind of a variation of the 3 screens in a cloud theme. And then also it brings in a variety of other systems and devices into the picture. So when we think about what these types of solutions are really about, the way we're thinking about them is that they are systems. What's interesting is that we have extended the scope of the systems we're building to include more components, to include physical things. You can think of them as peripherals, if you will. We're now able to build applications that have a lot more peripherals attached to them. And therefore, we can do a lot more interesting things with those systems. So one of the other things I wanted to point out is that if you take a close look at this picture, you can see there's a lot of moving parts. There's a bunch of components here that I've kind of outlined at a high level that go into building out a backend for a solution like that door-to-door navigation service. And you can see that messaging plays a big part in that, because what's really happening is that we're moving a lot of data around. It is true that data and the volume of data that the Internet of Things is generating is already noticeable. Car manufacturers are coming to us and talking about petabytes of data that they need to move around from cars to back-end systems and vice versa. Not that everything moves up into the cloud, but there's a lot of moving data here. So we've started to think about this in terms of big data in motion. So a lot of the problems that we talk around big data and a lot of the technologies that we've developed for dealing with big data will be relevant here, but we'll need to make some changes in order to think about dealing with big data when it's moving. And when it's moving, in some cases, at very high velocity, and with many different counterparties that need to receive it and interact with it. So this is some of the interesting kind of dimensions of where the Internet of Things is driving new requirements on our technology, on the platform. Also, the timeliness of this information is important. So the near real-time aspect of many of these interactions requires that we really optimize for the latency aspect of things. And also for making sure that we're doing the right processing job at the right place, which means that we're going to be more and more doing distributed processing. Processing is going to live wherever it needs to live to meet the timeliness requirements of the job and to minimize the amount of data that needs to get shoved around, which can be expensive. So now we're talking about more and more moving toward a distributed systems architecture when we build our applications. When you do that, you need a way to connect the components of your application in a way that's location transparent, in a way that allows them to be scalable. We have messaging essentially kind of called for at the core of the application when we start to talk about those types of designs. So again, you see messaging a lot in this picture, but it's a much bigger story around how we're connecting up distributed applications in order to deliver on the Internet of Things. So stepping back and squinting at a high level, this is what the stack looks like, what I call the IoT Cloud Platform stack. It's an abstract model. I haven't really plugged in any particular services or technologies here at this stage. I will in a second. But just to kind of walk you through this flow, on the far left-hand side under A, you've got devices out in the world, which are either IP-capable devices, in which case they are often able to directly interface with cloud assets, or they're not IP-capable, in which case there's likely going to need to be some sort of a local gateway that they interface with that in turn proxies their interactions with cloud services. So we see those two models. Either model ultimately results in telemetry and command and control channels being created between the devices and a cloud gateway. So this cloud gateway is the thing that terminates protocol and connectivity into the cloud, and in turn, on the backside, exposes telemetry and command and control interfaces to services that are living behind it. And then I have just sort of two high-level placeholders here for the kind of components that we see on the cloud side. One is what I called custom code, so your own custom logic. The other is more kind of higher-level developer services, things like storage and other capabilities that you'll leverage to build your application, building block services, if you will. And then finally, you have third-party applications and services and enterprise systems living somewhere else that you also need to interface into this system. All right, so the custom code options that we have in Azure, fairly rich. We have websites, VM roles, mobile services, cloud services, and you can certainly run your own external code and connect in to services running in Azure. A lot of people do that. We also have on the cloud platform services side, this is not an exhaustive list, but just some of the ones that we see come into play with some of the IoT engagements that we have. Certainly the various storage options, Azure databases, table blob storage. I've already mentioned Service Bus. Service Bus doesn't just live in that cloud gateway, but also kind of as an integration layer for integrating external components into the system, and also for providing resiliency and scale within the system itself. HD Insight, media services, BizTalk services, there's a long list I could have put here. Coming back to the cloud gateway, what is actually inside that gateway? I'm going to drill into that quite a lot more in the coming slides. But at a high level, I wanted to call out two patterns that you're going to see reflected in the later slides. One pattern is where either the field gateways or the IP-capable devices are directly connecting into, in our case, Service Bus, or whether they're connecting through some sort of a custom gateway role that customers have implemented in order to handle a custom protocol or to do some pre-processing before the commands or telemetry messages are transmitted. So we definitely see both models. And one of the things that you'll note in a little while as I go through the architecture that we are recommending is that we are building in actively support for the second model as well as for the first. So our assumption is not that every device in the world connecting to the Azure cloud will directly connect to something like Service Bus. So what are the device gateway challenges? And now I'm going to start talking about that cloud gateway as a device gateway. You'll see why in a little bit. First, with the connectivity side of things, there's a set of challenges. And there's another set of challenges around messaging that I'll talk through in a second. As far as the connectivity aspects, there are 4 big problems that we see. The addressability problem. How do I deal with devices that are not on IP, that are not capable of IP? How do I deal with location transparency, being able to access devices no matter where they're living, even if they're on networks that I don't control? How do I deal with the fact that devices can be online or offline at different times or roaming and may change their address or their location? Those kinds of problems. Some of these are things that we've dealt with in the enterprise context already for some time. Dealing with these problems in the case of small devices is a little bit of a different challenge, but it's the same core set of issues. Heterogeneity, there's a variety of different types of heterogeneity or diversity that we see out there on the client side. In the IoT case, it is huge. The number of types of OS and firmware that are in use for IoT is staggering. And then we have to deal with things like power and network constraints that are special in the case of small devices. Sometimes devices are operating on batteries that have to last for years. So we have to be very careful about the kind of expectations we have on those devices. And then protocols. Security, from a security perspective, there's a whole world of concerns that are starting to surface as more and more people understand the special challenges of dealing with small devices. I'm not going to talk a lot about those here, but we're doing quite a bit of work in this space. And this is something that some of the patterns that I'm going to show you actually help to reduce and simplify the security problem. And then efficient scale. So dealing with devices often requires dealing with connected things in very high numbers. So we have customers coming to us with millions of connected things that they want to hook up to Azure and integrate with backing services. So from a messaging perspective, the challenges are around the common patterns, the common interaction patterns between services and devices. And there are many different nuances here, but at a high level, we bucket those into the telemetry pattern, which is moving data up into the cloud. And that involves things like collection, filtering, dealing with how do I handle very high throughput when I'm dealing with aggregate volumes from large numbers of devices that amount to thousands, tens of thousands, hundreds of thousands of messages per second. How do I process that? And things like ensuring that an alert gets to a back-end role at a higher priority than a telemetry message, which may just be one of millions of updates from a temperature sensor. So how do I distinguish between those two and ensure that the really important messages get through? That's quality of service. From a notifications perspective, we have the problem of how do we address individual devices or how do we address groups of devices, effectively the pub-sub problem, spread over a very large population potentially. And then with command query and what we call inquiries, which are sort of service invocations from devices up into the cloud, there's the problem of correlation. How do I correlate these streams over messaging channels? And how do I do things like sessions and batching and all that kind of thing? So I'm going to start with the connectivity aspect and first talk about what I'll call the default IoT connectivity model, the way that we see a lot of customers thinking about how to connect small devices, sort of as the default. And that is to think about those small devices as really just like any other general purpose computer, which is that we tend to think about general purpose computers as using a sort of classic recipe whereby we give the machine an address, a routable IP address, and then we expose services on that host so that it can be remotely controlled and queried. And then we enable access on some sort of a bounded network domain. In this case, we see most customers looking at VPN technology in order to enable that. So this is kind of, if you think about it, this is a fairly low-level network layer approach to how you would connect with devices. It has some issues. The addressability problem that I mentioned before certainly can be solved with this. However, it does require a network layer intervention. So you have to have some amount of control over the network, or you need to be able to run something like a VPN, a virtual VPN appliance, or a VPN gateway component somewhere out there in the world. And that can be problematic or costly. For devices that are loosely connected, this sort of a model doesn't really work. From a security perspective, VPNs are built such that by default, every protocol that can be routed over Ethernet can flow, and between any two nodes in the VPN. Of course, you can go in and create rules to prevent that, but that is a complex and somewhat fragile process to manage. Essentially, VPNs are designed to control access at the IP address and port level, not at application endpoint level. So there's a lack of granular authorization that VPNs fundamentally do not solve. And then finally, from an efficiency perspective, many devices are not capable of running a VPN agent or participating in a VPN because of resource constraints of one kind or another. And VPN infrastructure is fairly expensive. So there are a variety of reasons why this is not a slam dunk. We've seen some customers who have worked very hard to make this work and gone to great lengths to get something running. But oftentimes when we present them with an alternative, they're thrilled to know that there's another way. So I'm going to talk a little bit about what that other way is. It's a method that we've written about. A fellow on my team, many of you probably know, Clemens Vasters, has written a very nice article about this called Service-Assisted Communications. You can find that on his Subscribe blog on Channel 9. And that goes into great detail about how all this works. But I'm going to take you through this at a very high level just to sort of show you the mechanics of how we think about connecting devices securely to our cloud. So if you imagine on the right-hand side, this little blue box is a device. It's on some sort of an IP network, and it's protected by a NAT or firewall router. And it needs to communicate with the cloud gateway. Using the service-assisted communication model, what happens is that the device initiates an outbound connection. That outbound connection is treated by the NAT or firewall device. Well, the device doesn't actually listen for unsolicited traffic. The NAT or firewall device simply maps a port automatically, since this is an outbound call. And typically, we can do this over port 80 or 443. So there's very few networks in the world that won't allow outbound traffic over those ports, allowing the device to establish a socket connection to the gateway. The key point being that no inbound ports are open, and the attack surface is minimized. Then on the cloud gateway, we expose an access-controlled API for commands and for query operations on that device that backing services need to perform. So we have a well-known DNS entry for this particular address where this device's interface is located, and the cloud gateway acts as effectively as a proxy for any access to and from that device. So this method, service-assisted communications, actually has a lot of advantages. I'm not going to go into it in great depth. Again, there's a paper describing it. But the key thing to note here is that we didn't have to do any network-level intervention. Once in a while, you'll get into a situation where you'll have a device out there in the world that won't allow port 80 or 443 outbound. Those are very rare circumstances, and we treat those as sort of exception cases. But for the vast majority of cases, this approach works very well. Once we have that outbound connection, then we can wire up a bidirectional messaging channel over it. And that's kind of what I'm going to talk about next. So how does it work? Concretely, devices connect to the service bus today using one of the open standard protocols that the service bus supports, either AMQP 1.0 or HTTP, HTTPS. Those are both natively supported by service bus already. AMQP 1.0 has client libraries for a variety of platforms and languages. We can help you with that if you have questions. MQTT and CoAP are protocols that are being discussed quite a bit for connecting devices in the Internet of Things space. These are things that we expect to invest in going forward. And for now, we're helping customers to implement custom gateways using an adapter model that we've built out. So anybody that needs to use one of these protocols can do so with some guidance from us. The sockets that get created are secured via TLS by default, but we do recognize there are scenarios where TLS is too heavyweight for a device, and we're working on some lightweight variant for that. Essentially, the way that the service-assisted connectivity model works relies upon the existence in the cloud of a virtual set of endpoints for that device that it can interact with reliably and consistently as its source for commands and its destination for all outbound messaging. And we've kind of abstracted that in the form of talking about it as a device inbox and a device outbox. So using brokered messaging, using a product like Service Bus that has queues and topics and other capabilities for durable messaging, we can easily implement an outbox and an inbox on a per-device basis and effectively give every device a well-known endpoint for it to communicate with for all interactions with backing services in the cloud. So this is effectively the way it works. The device sends telemetry and alerts up to its outbox in the cloud over one of the supported protocols, and it receives commands and queries via pulling messages off of its inbox. Correlated patterns, if you need to implement a request-reply pattern, can be easily implemented on top of these two messaging channels. Most importantly, the device knows and has access to only its own specific inbox and outbox endpoints. And we have an auth model that we use to restrict that access. So that really provides already a great simplification in terms of the security model and the surface for vulnerabilities. Because effectively what you've done by taking this kind of approach is you've taught the device that there's one trusted counterparty that it interacts with, and that means that that device does not need to listen in a promiscuous way for connections or messages from other arbitrary sources. That dramatically reduces the security challenges of dealing with small devices. And it also allows you to move some of the work, some of the heavy lifting of protecting devices out to servers in the cloud that are very well resourced and fit for the purpose. All right, so that's about connectivity. I'm going to talk a little bit about the messaging side of things. I mentioned the connectivity challenges and the messaging challenges of implementing a device gateway. So on the messaging side, the two broad patterns that I'm going to talk about are telemetry and command and control. First with telemetry. This is an abstract picture, but it shows you how you can use pub/sub messaging, publish-subscribe messaging, such as what we provide in the Service Bus, to implement a simple routing capability. Again, this is very simplified. We have much more complex implementations that customers have built, but I'm just trying to get the concept across about how pub/sub is actually used for telemetry. And one of the key things that we see is that customers often have multiple downstream components that need to consume telemetry data. So those components might be, in this case, I've got an example of an alert processor, and that's a different role than the storage preprocessor that's going to be taking all of this telemetry and pumping it into something like Azure Table Storage or Blob Storage for later analysis. So if you have these types of requirements where you have multiple back-end roles and each role needs to see the telemetry stream or a slice of it, then pub/sub is a great way to do that. You can effectively create a rule using these filters that we support on the pub/sub topics. And based on that rule, you can determine that the following message is an alert, and that needs to be routed to a subscription that is going to be read from by the alert processor. And you can determine that other types of telemetry is regular data that needs to be pumped into storage. This allows parallel processing. It also allows different levels of quality of service. Remember, I mentioned before that some messages are more important than others. This is one way that you could implement that. By doing this type of an approach, you can actually you can actually use different methods in terms of how you do receive from the alert subscription, so that you can have a sort of a guarantee that every message you pull off of that queue or that subscription has actually been consumed fully by your receiving application before you delete it from the subscription. Those types of things. It's a little bit more costly method for receiving messages, but it warrants that cost in the case of an alert. And there's a variety of other settings, for example, of that type that you can use. So then generally, just leveling and balancing the load is one of the things that you get from this type of a model. So if you have an alert processor that's not keeping up with the number of alerts, then by having a brokered messaging intermediary, you can count on that broker to store those messages durably until your processing role catches up. So that's kind of one of the key aspects of using messaging to build scalable and reliable systems. Most of you are probably already doing that today in your applications. Okay, routing commands with the Azure Service Bus is similar. So in this case, we've got components on the right-hand side, the senders, that need to send notifications, command messages down to a set of devices. And the way they do that is they send into one or more topics, which have filters that can use cues, like can use information such as tags that allow the topic to filter those messages and deliver them to just the devices that need them. And so here I've got an example of devices that have registered as a Model A, a Model T, and in this case, device 3 just has its own identifier. So device 3 is a Model T. He's going to get all messages that are either from Model Ts or directly for him. Device 1 and 2 will get either Model A or Model T messages. So this is an example of how we use pub/sub messaging to deliver commands to devices. We can also do things like set delivery timeouts. So if I'm standing in front of my car trying to open the door, that command to open the car door is actually only significant for a certain amount of time. After a certain delay, it's no longer relevant. I'm not going to be waiting for my car door to open any further. So oftentimes we will use things like TTLs in order to implement those types of timeouts. Also dealing with spotty connectivity. Oftentimes devices are loosely connected. They are on unreliable networks or they're only periodically connected. So once again, the idea of having a durable broker in the middle is really valuable. And then we have the ability to traverse NATs and firewalls securely using the method that I described before. Okay, so those are kind of general models for how we would use pub/sub messaging in the case of IoT. What I'm going to talk about now is how this all comes together, because in reality, when we work with customers on these types of architectures, there's a lot of pieces that need to get built or implemented around the messaging core in order to truly implement a scalable and robust device gateway. What you're seeing here is a reference architecture for such a gateway. This is a picture of the complete reference architecture that we've developed in the course of helping customers implement real scenarios on Azure. But it's not just a picture, it's something we've actually built and that we use as a source code-based engagement tool. We have an internal code name for it. We call it Reykjavik, after the capital of Iceland. That's actually due to Mary Jo Foley, a famous ZDNet blogger, who was complaining about our code names, and so we asked her what would be a good code name. She didn't know what she was naming at the time, but we decided to honor her with this name. At this point, we're using this guidance, this code-based, source-based engagement tool selectively with specific customers based on projects that come to us through MCS or partners. So this is not something that's broadly available at present, but we're using it with projects that need bidirectional communications to devices at the scale of hundreds of thousands or even millions of connected devices. And while we've had to provide some substantial guidance as a part of that, again, the core of this is the service bus messaging infrastructure. And what we found is that it's actually quite possible to deliver a very scalable and full-featured device gateway by leveraging the features that we already have in the production service bus today. Now, we're actually using this process to learn and to figure out what we need to do to further optimize our messaging infrastructure for these scenarios. And that's a very active, ongoing process, and one for which we are still, we're still looking for and extending our engagements with customers. At a high level, what's new and different? There's 4 big things that are new and different in this architecture beyond the core messaging. One is the custom protocol gateway that you see up on the top right-hand corner. This is for making it possible to plug in protocols that we don't natively support, or purely custom protocol implementations, while still leveraging a lot of the scale-out infrastructure that we've built to host our own protocols. The next one, number 2, is the adapter layer. This is for telemetry. We have a sort of a telemetry pump and an adapter model for extending that telemetry pump to interface with common downstream services that, that we see customers interested in routing to. So this list is a representative list. Today, we've actually implemented the HD Insight adapter, the Azure Storage adapter, and as you'll see from Paulo a little bit later, we have an Orleans adapter. You probably don't know what Orleans is. It should be Orléans. I need to say it correctly. Does that help? No. That's because it hasn't been announced yet. But Paulo's gonna spill some of that. The command API host is another big piece, and this is one in which we're basically helping customers do the translation between an API that is written specifically for their devices and the generic command routing infrastructure that needs to get implemented to handle some of these messaging challenges I mentioned a minute ago, addressing specific devices, groups of devices, and so forth. We've sort of abstracted all that away by showing customers how to write a simple command router and host a custom API on top of that for their devices. And then finally, we have a provisioning service and metadata store that does the work of setting all this up and scaling it appropriately for the solution. Okay. Looking a little more deeply into the architecture, some of you may notice similarity to an article we published a couple years ago. Clemens Vasters wrote an article for MSDN magazine called Service Bus and Things in June of 2012, and followed it up with another article which actually provided not only some architectural guidance, but actually some code, some sample code, and some implementation of that model. And a lot of what we've got here today and what we're showing you is a realization and an evolution of what that article talked about. So in the last 2 years, we've had the additional experience of engaging with a number of actual customers. And that is really what has caused this to evolve into what you see today. Implementing the service-assisted communications model with a set of scaled-out topics. Here we have, in this picture, you can see a set of topics called ingestion topics. That's for the telemetry flow. And another set of topics that I've labeled command topics. That's for the device command and control flow. So as you can see, it's a little bit more complicated than what I had in the blue box, because you actually have to think about scale. You have to think about partitioning load across multiple topics in order to scale this. And this is part of a model also that we found a lot of customers haven't really had much experience with, but we're quite comfortable with given the experience we've had building and running cloud services at scale. And that is that inevitably, whatever architecture you build at some point runs into a scale limitation. And what you need to do at that point is to understand what are the units of scale that you can comfortably manage. Once you build out those units of scale and understand what a particular unit of scale can do, then the problem can be reduced to replicating those units and managing how you distribute load into those units. So this sort of scale unit model is fundamental, and it's at the core of what we've implemented in this architecture. And it's also one of the things that some of the customers we've worked with have found most helpful, just sort of understanding how to think about a design like this in terms of scale units. But effectively, we've got a model here where there are two high-level roles. One is the master role on the left-hand side. The master role handles the deployment of this infrastructure and also the provisioning of devices into this infrastructure. So ensuring that those devices are balanced appropriately across that infrastructure. Then the other role is the partition itself. And the partition itself is a set of resources that's designed to serve a particular population of devices. So at a high level, you kind of can see that what we've done here is taken the existing service bus artifact and built out additional capabilities around it in order to deliver the full device gateway. Okay. So I'm going to jump into a demo in just a moment. But before I do that, one of the things I want to point out is that with this type of an architecture, global coverage is achievable. And this is something that we've found is very important in the IoT, because a lot of the companies that are early in really thinking hard about how the IoT can be an advantage for them or trying to get ahead of disruption in their industries are big global players, big global product producers, OEMs, manufacturers, folks who have global operations and really need to think about this from day one in any architecture that they build. So essentially the way that works with the kind of architecture we just described is that we take those partitions and we can spread them across the Azure data centers across the globe and have multiple partitions in each data center, but essentially achieve that kind of global presence. And that allows for the processing that needs to happen for a device to happen relatively local to that device's operation. The reference architecture supports up to 1,000 distinct partitions at present, and the kind of decision about how many partitions and the distribution of them is driven by these types of factors. How much data volume are you going to be dealing with? What are your concerns and considerations around business continuity? And then legal considerations are often very prominent, especially in Europe and Asia, in terms of data not being able to leave sovereign domains. Okay. So I'm going to switch over to a brief demo. How am I doing on time? Pretty good. Okay. I'm going to show you around a deployed instance of one of these device gateways. This is one that we use for test and demo purposes. In this case, the devices that you're going to see are emulated. We are limiting, and we've just limited it to a deployment of 10,000 devices. The point of this demo is to show how it works, not to do a scale test. And for the purposes of understanding how the device gateway is put together and how back-end services interact with it, it's not going to be terribly important what's happening on the device in terms of the particular platform and what the capabilities of that platform are. One of the things that I'm going to show you in that emulator is that the device client here can be very, very simple. So from that, it'll be pretty easy for you to see how that could be extended to very small devices. All right. So on the left-hand side here, in the Server Explorer, I've got the assets that support this device gateway pulled up and opened. So first of all, taking a look at the cloud services, we've got this demo, which we call the Fabricam, where we've labeled it Fabricam, broken down into one master deployment, which is this guy here, and a variety of partition role instances. And each of those is in a different geographical region. So this is in the East US. Here, this is North Europe. This is in Asia, West Europe, and West US. So we've basically done a tour around the globe and put one of the partition roles in each of the regions. And then we have the one master role. So these are going to have roughly 2,000. Each of the partitions is going to have roughly 2,000 devices in them. And then in addition, what we've got deployed here are the service bus namespaces and the storage accounts that support the functioning of those partitions. So there's a matching service bus namespace and a matching storage account for each of those partitions, as well as for the master role itself. So how did all this get deployed? So this was all done using a tool that we've written called Device Gateway Deploy Tool. And it's part of the Reykjavik project code. And just to show you at a high level, again, what's happening here is that this deploy tool makes everything that you see here, all of the cloud services, the service bus namespaces, the tables, and the storage accounts, including all of the queues and topic infrastructure, all of that gets created by the deploy tool. It essentially makes partitions for a set of devices based on a set of inputs that are provided to the tool. The most important inputs to that tool are down here, where we're creating a partition, and we've got a list of inputs around the device count, the number of messages per hour that are expected, the size of those messages, both on the ingress and the egress side. So basically, we take in inputs that represent a load model, and based on that load model, we produce a deployment of that partition to serve that population of devices. So let's take a closer look at what's actually been deployed here. So I'm going to go into the first partition that we put in the East US, and I'm going to take a look at the topics for that. And what you see here are the topics that got deployed when we fed in a model that was based on roughly supporting 2,000 devices per partition. What it did is it produced a set of ingress topics. And here, I think we have on the order of 20 ingress topics. So roughly 100 devices per topic was where the model landed. Each of these ingress topics, if I go in and look at what's inside of it, has a set of subscriptions associated with it. There are 3 subscriptions in this model, and it could be more. This is completely customizable, but it was something that we just wanted to show how we think this will typically be used. And then customers often take this and sort of elaborate on it quite a bit from here. The first subscription is a diagnostic subscription, and it's effectively off at all times unless for monitoring or troubleshooting purposes, there's a need to go in and get a separate feed of exactly what messages a particular device is sending. So this can allow effectively like a troubleshooting tap on an individual device. You can see all telemetry coming from that individual device by subscribing to this, this subscription. Also, we have a subscription for relates to. Relates to is, if I go in here and look at the rules, this has basically got a filter associated with it that says, if there is a relates to property on this message, then I want this message to be part of that subscription. I'll show you what that is in a minute, but effectively it's for implementing the command and control request reply pattern. This would be the way that a device actually sends back replies to commands and queries that it has received. It tags that with a relates to property, and then it can be used, it can be siphoned off and feed into the command API to complete the operation. The table history subscription has a rule which basically says everything that isn't relates to, I'm going to pump into this particular subscription. So not exists, user.relates to. What this is a complete capture of all of the telemetry coming from all of the devices on that topic. And that's going to feed into the telemetry adapter and the table storage pump, the table storage adapter that we've got. I'll show you that in a minute. So those are the in topics. Let's look at the out topics. These are for command and control. So for the out topics, you can see we have, it's not scrolling for me, a very large number of individual per device inboxes. So every device in this partition will be married to a particular subscription that is its inbox for commands. So what we've effectively done here is we've built this inbox and outbox infrastructure that I mentioned earlier, and we've scaled that out for a target community of devices at a certain, with a certain set of assumptions of what that scaled out infrastructure needs to be able to support and do. We haven't yet done anything to make it specific to a particular application, really, other than, I mentioned the telemetry adapter piece. But really, at this point, it's a generic plumbing for connecting devices and services. and implementing all of the patterns that I talked about before. So that infrastructure is already there. Now, what happens on the client side and what happens on the service side? So to talk about that, I'm going to walk through a little bit a sample application that we have for a space heater. So this is a really simple kind of introductory application that we provide as part of this package that just shows how to use the system. So the first thing I'm going to show here is the device emulator. Inside the space heater device emulator code, I'd like to just demonstrate or walk you through sort of the simplicity of this code. So there's a very few set of properties that this device knows about, including whether or not its fan is on or off, whether or not it's heating, what temperature it's heating to, and what speed its fan is going at. Effectively, we've got a dispatch switch. This is basically a simple loop that goes through, and depending on the command that the device has received, it will invoke the handler for that command. And then if I go down and look at the individual commands, like in this case, we're switching on the heater and telling the device, the space heater, what temperature to set. You can see that it's a very simple key value pair-based message exchange that's happening here. So I'm just pulling out the value of some properties that have been sent down on the message and then sending back a response. This is a switch heater reply in which I give the current state after having implemented the change to the heater setting. Okay? So there's really nothing complex going on here. This is a very simple message-based exchange. There's no heavy framework. There's really no framework at all. It's a very lightweight message-based process for interacting with your devices. You can also see how with this sort of code that this would be fairly easy to transpose into a smaller device. We're not making use of any kind of more advanced functions that you might find problematic if you were going to implement this on lower power devices. The place where that might come in is, again, around TLS and some of those types of things, but we also have some work going on there. I'm going to dig into the telemetry send routine a little bit here. So 53. This is where the device, on a periodic basis, roughly once every 30 seconds, will send a telemetry package and update the service on its current state. I've already mentioned the relates to field that I showed in that particular subscription rule, but you can kind of see where that comes into play here. When you do a switch fan async, the fan speed and the fan on-off setting gets updated, and when the response to that message processor is delivered, it sets a relates to property on the response message, and that's how that ultimately gets routed back through the ingress topic to the command API. So let's take a look at the command API side of this. That's here. And so this is an ASP.NET controller. This is using a simple web API. Already open. And effectively, what we've done is implement simple web methods for every operation that the device can support. So here we're actually putting the device configuration on the device, getting the device condition, switching the heater fan. All of these things effectively translate down into a message that gets sent over that command API. And some of the infrastructure for this has been delivered through a common library that we included with the package called the command API. So there's a command API infrastructure, it's down here, that takes away some of the underlying plumbing so that you don't have to actually worry about that in your code. And what that results in is that the command API could be a simple RESTful API, and you can use, for example, whatever security means, whatever security paradigm you'd like for securing that without having to deal with any of the lower level plumbing. And then the last thing I'm going to do is just show you really quickly where all this data landed. So if I go down to the storage account here, and I show the tables that are in that partition. Here's a table that's collecting all of the telemetry updates coming from those devices. And this is a collection of telemetry updates that have been collecting ever since we sort of staged this demo a few days ago. So you can see that what's coming in here are individual updates every 30 seconds from devices that are updating each of these properties that we saw that the devices know about. Okay, so that's the demo of the device gateway. I'm going to turn it over to Paulo in just a second here. In fact, I think I'm going to turn it over to Paulo now, and then I have one more slide, and we'll close. Thank you.
Okay. So thanks, Todd. So my team decided to invest a couple of weeks to build the prototype called Tribble of a real-time analytics and IoT solution that is able to consume messages coming from emulated devices and generate alerts that can be consumed by an operator dashboard. So Tribble has the same architecture as Reykjavik, and in fact, the final goal is to integrate the two projects, and in particular, to transform the processing layer that we'll see in a minute, which is based on Orleans, into a telemetry adapter for Reykjavik. So Tribble is comprised of the following modules. We have a service gateway that translates between the device protocol and the backend system. In particular, this module receives messages from devices through HTTP and send messages to service bus topics and queues. The ingress messaging layers that handle messaging between the service gateway and the backend system. So in particular, this layer can use multiple adapters, but in this release, we implemented an adapter for the service bus topics and queues, of course. And then there is the processing layer that represents the core of the prototype along with the service bus. So to implement the processing layer, we decided to use two technologies built by Microsoft Research. The first one is Project Orleans that we'll see in the next slide, and the second one is Trill. So the processing layer is responsible to process messages coming from devices through real-time queries and generate alerts. So Project Orleans is a library and a framework that provides an object-oriented programming model for building large-scale, stateful, and distributed applications both on the on-premise and in the cloud. So Project Orleans provides an implementation of the distributed actor model. So actors are defined by .NET classes, and at runtime, actors are isolated, single-threaded components that encapsulate both the state and the business logic. So in our demo, we'll have an actor for each device. Going forward, we would like also to create more complex actors that are able to join streams of data coming from multiple devices and that are able to generate alerts based on a combination of events across multiple devices, okay? So actors communicate between each other in an asynchronous way, okay, through asynchronous calls. And at runtime, they are automatically and transparently distributed across multiple servers by the runtime, okay? Actors are defined and uniquely identified by a long or a GUID. And the most important thing is that whenever a request is sent to an actor, which is at the end is a .NET object, okay, the runtime of a Project Orleans is going to instantiate that object on one of the services that compose the cluster. Just to give you an idea, an Orleans cluster on Azure is composed by multiple instances of a worker role, okay? So there are a lot of other functions and features provided by Project Orleans, okay? So like, for example, an observable and observer programming model, also timers for scheduling specific activities, and so forth. So I really encourage you to go and attend the session on Project Orleans today at 5:30. So let's look at the architecture of the demo. So first of all, we chose to simulate two kind of devices. The first one is on and off devices, let's say so, like a door that can be open or closed. So the state of these kind of devices can be a 0 or a 1. And one of the two is considered as an abnormal state, okay, that generates an alert. The second kind of device is a value threshold devices. Like think about thermostats or temperature sensors. In those cases, the normal value should stay within a specific range, which is defined by a minimum and a maximum threshold. So this is the architecture of our demo. First of all, I'm going to use a Visual Studio load test to send messages to my gateway service. The gateway service is implemented as an ASP.NET Web API RESTful service and runs within a worker role inside Katana. So this service receives messages and send those messages to queues or also to topics. Then we have yet another worker role called ingress worker role that is hosting the adapters. And in this case, it creates a listener for each of the queue. As you can see, all the information about queues and devices are in a table storage. For each message that is received from a queue, this message is sent to a so-called grain. Okay, the grain is the equivalent of actors, okay, in Project Orleans. So as I said before, we have a grain for each device. And that grain is identified by the device ID. So it's a one-to-one mapping. So the grain inside is running some real-time queries implemented with Trill. Now, what is Trill? Trill provides an in-memory temporal analytics engine and is yet another technology built by Microsoft Research. But this technology in particular is not yet released. It's still under construction. Still, my team thought this was a good fit, okay, for this scenario, so we decided to use Trill. For those of you that had the chance to work in the past with Streaming Side, the programming model and the queries of Trill, they should look very familiar, because give or take is exactly the same programming model. So when the device grains run these real-time queries and find an alert is sent to a topic, okay? And the topic, as you can see, has a different subscription, one for each possible kind of events, okay? And there is also a subscription called auditing that has a filter that is always true, that this collects all of the alerts generated by the processing layer. And I will use my tool, the Service Bus Explorer tool, just to simulate an operator dashboard, okay? So let's switch to my wait a second. Yeah, I know, it's not the right one. Here we go. So, first of all, as you can see, I have here 10 ingress queues. Okay, so this is the namespace used by my Tribble project. While I have a topic for alerts, and in fact, this is called alert, with a few subscriptions, an auditing subscription with a rule that is always true, while for the other subscription, like, for example, below mean threshold, if we look at the filter, you can see that the filter is even equal below mean threshold. Now, let's look at the code first, and then I'll show you the demo. So this is the code of my gateway service. It's an API controller. Is reading information from table storage, so reading information from queues. As I said, in the table storage, I have two tables. One is called devices, and as you can see, the configuration column contains the configuration of each device, so metadata plus the queries that I want to execute on that device, and this is expressed in JSON. And same story for queues. There is a separate table and with a configuration column, which contains the configuration for that queue, and in particular, the devices that can send messages through that queue. So at runtime, the gateway controller exposes a single method called post, which receives a message and individuate the right queue and send the message to that queue. The ingress layer that runs on a different worker role, let me show you this. We have 3 different worker roles. So one is the gateway, the other one is the ingress, and the third is the Orleans one that contains is the processing layer. So the ingress messaging helper is responsible for reading messages out of queues, okay, and invoke Orleans actors or grains. So the very first thing that this layer does is to create the Orleans client, which is necessary to talk to communicate with actors. And then these instantiate the service bus input adapter. As you can see, these create a listener for each of the queues. So if we go to the declaration, here we have a main loop where I'm using a receive batch async to receive messages in a batch mode from a specific queue. And for each message, I'm going to execute a delegate. So this delegate, if we scroll down, is using Orleans, is using a factory, okay, to get a reference to a so-called grain. The grains in Orleans, they are defined by, let me show you, by an interface. And this interface, oh, sorry, this is the implementation. The interface is made of asynchronous methods and properties, so they all return tasks. The implementation of the device, very quickly, and then I show you the demo, yeah, I know. So it's running some real-time queries. So the real-time queries, just for your knowledge, let me show you these, and then we show you the demo. I'm not going to describe this, but for those of you that are knowledgeable of Stream Insight, you can recognize the same programming model. Okay, let's jump to the demo because we don't have time. So I'm running this load test to simulate, messages coming from devices, and I'm going to use my tool, Service Bus Explorer, to create a listener, for example, on the auditing subscription. I can specify a maximum concurrent calls, refresh interval, prefetch count, and I start. And at this point, I should start receiving. Oh, let me show you what's going on. Oh, let's do this way. Okay. Okay, as you can see, I'm starting receiving alerts. Okay, if I switch to the tracking, to the messages tab, I can also look at the metadata of the alerts. So for example, in this case, the event was a below mean threshold because the low threshold is 10, the previous value was 17, and the actual value is 9. Okay, so I have not only the data of the event, but also the metadata of the device, like the name, location, and so forth. Okay, we can switch.
Okay, thank you very much, Paulo. And I just wanted to put this back up so that you can see how to reach us. Take a look at the session at 2 o'clock today on Friday. If you want to learn more about high-scale messaging with Service Bus, Abhishek Lal will be giving that. Take a look at Clemens Vaster's Channel 9 blog for more information about our work in the IoT space. And we are looking for customers and partners who want to engage with us on some of these IoT patterns. If you think you're in that category, please don't hesitate to reach out to me. Here's my email address. You can contact me directly and we'll follow up. Thank you very much, and I apologize that we went over the time today.